Like I said, my name is Henrique Queiroz. I'm a mechanical engineer from Cefet here in Brazil, and I'm going to present to you our initial findings of the work entitled Evaluation of Durability of 3D Printed Multi-Material Parts for Potential Applications in Structures Exposed to Marine Environments. This is a conference in additive manufacturing, so I'm not going to spend too much time here on what it is. Suffice it to say that since it was invented, it has been an increasingly paradigm shifting technology, right? Because it basically allows you to decouple the price of the part from its complexity, because you can just print it all at once. And out of these the seven main categories, right? So we have the sheet lamination, direct energy deposition, many different technologies. However, the one that is easiest to use for most people is, of course, the FDM, right? So why do we use FDM? The ease of design, and of course, the economy. You have very, very cheap machines that you can buy many of them for the price of a single one of a different technology. And reduced environmental impact, especially on the type of polymer that you use. And like I said, cheaper machines and the types of materials. So when you work with polymers in 3D printing and FDM 3D printing, there is a very large family of products, right? And they vary pretty significantly between the structure of them. They can be semi-crystalline, they can be amorphous, and they also vary very significantly on the mechanical properties that they have, right? And so when you go towards higher performance, of course, you also increase the cost. But there are two materials, I'm sure you are well aware of this, that are the most common, which are PLA and ABS. So these are the materials that most people that are doing normal printing are using, right? And so why did we choose these materials? For these reasons, right? Because they're very easy to find, they're very cheap, and they're very fast iteration. It doesn't really hurt the pocket too much. And so what application are we using it for? So there is a project called the PMPAS project, which is part of the Brazilian Navy. And so they have a kind of sonar, right? They use, it's in the image right now to the right, and they use to have an acoustic monitoring of the landscape, right? And so they use this coupled with military projects, even in the petroleum industry, right? And so parts of the structure are 3D printed, have been 3D printed recently. And so what was observed is that the PLA printed parts, after long exposure to the marine environment, they come back deteriorated, right? And so the idea was, what if we used the 3D printed technology to create a hybrid material, right? So you have the PLA or ABS, and you also have structures that are essentially sandwiches, right, of PLA and ABS. Now, why do that? Well, if you look at the literature when it comes to FDM, both for ABS and PLA, what we see is that ABS absorbs less moisture, and it tends to maintain its mechanical properties much more effectively than PLA. PLA is very significantly affected by the marine environment, aging, right? Not even marine environment, just like normal water environment. And so these are the printed parameters that we used. And so we fabricated these materials, right? And so what we did was we altered the number of ABS and PLA at the same time. So we increased or decreased ABS and increased PLA. And so we tried to find an optimum point when it comes to the mechanical properties, both for tensile and flexion, and at the same time, maintain the properties as much as we can in the aging environment. So how did we do that? Well, the aging environment was done actually in the ocean, right? So what we're looking at right now is one of the structures that the Brazilian Navy uses. And you can see the sensor right there, so that little blue tower. And so we used that we hitchhiked on that, right? Like a taxi to go to the ocean with our specimens. So we have our tensile and our flexural specimens, and we put them into these little nylon bags with perforations and inside of that vat structure. And so it allowed the ocean water to go through completely, right? And it was 60 days. And the depth changed, varied by approximately 19 to 25 meters. It goes up and down a little bit. And so we use that to do the aging of the specimens. So the testing was pretty simple. We have our classic tensile testing, right? With our 10 kilonewton load cell, 1 millimeter per minute displacement based on ASTM standards, and the same thing for deflection with 1 kilonewton load cells, just to have our baseline mechanical properties of the materials. And we also assess the failure modes with simple microscopy using an optical microscope. So to go straight here into the, I don't know if there's a, let's see if I can change it. There. So here we have our representative stress strain curves for the tensile properties. And what we can see right off the bat is that the material behavior didn't vary very much as a function of the aging. For instance, over here we have our ABS unaged, right, with the black square. And you can see it has a very classical ductile behavior. And when we look at the unaged specimen, it has almost the exact same behavior and very similar tensile strength. But when we look at the PLA over here, very similar behavior both for aging and unaged, and very similar final tensile strength. And of course, a much more brittle behavior compared to ABS, which is also known. But down here, we have all of our hybrids. And the first thing that we notice is that the behavior is very, very similar to PLA. So the brittle failure of the core was dominant, right, when it comes to the behavior. And the tensile strength was all very similar and, of course, lower to the neat PLA, which was also expected. Now, if we look at the tensile strength here in terms of the bar charts, what we see is that we have essentially two plateaus, right? We have the neat ABS on one side and the neat PLA on the other. Of course, the PLA is higher. And then we have a point of inflection here where one plateau becomes another, right? And there's a variation of approximately 17%. And what that means is that we found a point, this is interesting, where it doesn't matter much the number of layers of PLA. So we can go with less layers in terms of the sandwich structure, and it's not going to really affect the tensile strength too much, right? For the unaged case, that is. Now, interestingly, if you look at the aged specimens, we have the same behaviors, two plateaus, but we've essentially moved one case over with a variation of approximately 14% in tensile strength. Now, the reason for this is likely because this is the aged group, right? So the PLA that was in the middle got deteriorated more than the others, of course. And so it took more PLA to reach the same plateau, right? And it's not graphed here in bar chart, but you can take a look at the Young's modulus here. And you can see as a function of the aging, there was actually very small variation here, which makes sense when we look at the behavior. So the final strength was the thing that was most affected and not the actual rigidity. So when we look at the flexural properties, first of all, we look at the behavior and we see a different story, right? So the behavior is not as exact for all cases. It still is for ABS here, but for the other specimens, it varied more significantly. Now, the reason for this most likely is because when you're under 3-point bending stresses, right, you have your maximum compression at the top and your maximum tensile stresses at the bottom. So the outer layers are the ones that are doing most of the work under the 3-point bending loads. And of course, the outer layers are also the layers that are going to be more affected by the aging in the marine environment. And so the behavior was more significantly affected. And this was kind of expected, really. Now, over here, we have the same graph of the flexural strength, and we see a different pattern here. Let me just move this. And so when we look at the unaged flexural strength, other than this small dip here, we have a tendency of a quasi-linear increase from our pure ABS here to the pure PLA. And again, this is expected because as we have less ABS close to the outer layers, which are maximum tension and compression, we are going to increase the flexural strength. And also, the variation in the Young's in the flexural modulus is also more significant for the same reason, right? And when we look at the aged, oh sorry, over here, at the aged specimens, we actually have a generalized plateau. This variation between, for example, this case and this is actually within 10%. So you could technically call this a statistical plateau. It didn't matter much for the aged specimens, which is very interesting because you would think that you would have more damage in one PLA one ABS compared to the other, but they all aged right about the same. And so they reached a point where they stabilized, where the one layer of ABS at the outset, at the outer layers, damaged was damaged by the marine environment, but it reached a point where it basically stabilized, and it remains slightly above the pure PLA. Let's see here. So now to talk a little bit about the fracture of the specimens. So over here, we have two representative failure modes. These are tensile specimens, right? And you can see if this is the unaged PLA. And we see, of course, the voids of the printing deposition, which of course are always going to be there. And we also have some small imperfections between the deposition of the layers, right? This is expected. No specimen is printed perfectly. But when you look at the aged specimen, these these voids of the printed spaces are still there, of course, and they acted as the capillary ways where the water got in and started accumulating in these small fractures. And as time goes on, more water is in there, and it starts to debond the layers, which is the reason why the mechanical properties tend to go down more significantly for PLA than for ABS. Now, we see the same fractures for the ABS specimens here, but of course, we do not see this significant debonding. We can still see, for instance, here, this is the unaged ABS. And there's good bonding between the layers, but when we look at the aged, we can all see small cracks between the layers. Now, the interesting thing here is that the cracks are, let's say, more homogenized. You see them almost between each layer. Well, PLA, you have like two layers that completely debonded. And so this acts to sort of balance out a little bit, right? You don't have a significant debonding, but you have a lot of small debondings. And so it deteriorates, but it deteriorates slower, right, at a lower rate. And so this is interesting. This is one of the multi-material specimens that we tested. And when it failed under the tensile test, the ABS debonded for the PLA, and you can actually see water inside of it, like big drops of water, which is interesting to see. And so our general conclusions here is that the hybridization technique, which is to use different materials in the same specimen, was positive, right? It helped maintain some tensile flexural properties. For example, the 1 and 3 layers of the ABS maintain their properties pretty near the neat PLA. And we also saw a similar trend for the aged specimens as well. This suggests that in general, this idea that hybridizing PLA with ABS for marine applications is viable and it can be used. And the micrographs also revealed that, as expected, the PLA was more affected than the ABS, but we also saw how it was more affected. It had more localized debonding than the ABS did. And so there is room for general optimization there. And that's it. Thank you very much. I'm open for questions.